If you're ready now, Dan. Yes, great. So Dan is going to give the talk on modular denotational semantics for effects with guarded interaction trees.
Yeah, thank you, Sam. So indeed, and first of all, I would like to say that this is a joint work with Amin, Timany, and Lars Birkedal. Both of them you can find in real life at POPL'. So let me start by first breaking down the title. Our work is concerned with denotational semantics, as opposed to operational semantics, for example. And by denotational semantics, we specifically mean compositional, syntax-free, or almost syntax-free representations of programs and computations with higher order effects, for example, input-output or higher order store. And we want our approach to be modular in the sense that we want to be able to represent and reason about different effects separately and then combine that together. And finally, to achieve this, we introduced the framework of guarded interaction trees, which we fully formalized in Coq and applied to several case studies. So, as it might be evident from the name, our framework takes a lot of inspiration from the work on interaction trees. Interaction trees, which can be seen as a co-inductive version of free monads, it's a framework for representing computation with effects as possibly infinite trees. And most importantly, it comes with a very rich and honestly very impressive Coq formalization that has already been applied in many different examples and case studies and so on. However, that framework is tailored and designed towards working with first-order computations and first-order effects. And one way to look at our approach and our work is that we kind of provide a higher order version of that. And so to get you some idea about interaction trees, let's take a look at this example. Here you can see the tree that represents the following computation. The program first reads an integer from the standard input, and then based on whether that integer is even or odd, it outputs 0 or 1. So here, for example, in this branch, we input number 2. This is an even number, so we output 0, and then we terminate with exit code 0. So this interaction tree is parameterized by an effect signature. In this case, we have two operations, input and output, and they both come together with input and output arities. So for example, the input operation takes no arguments and produces an integer. So its input arity is the unit type, and its output arity is the type of natural numbers. Now, with this signature, we can see that the nodes in the interaction tree correspond to effect operations together with their arguments. And branching in the tree, well, that corresponds to the output arity. So, for example, the output arity of the input operation is a type of natural numbers. So that means that for each natural number, we have a successor that represents the continuation of this computation. Okay, so this is kind of a specific example of interaction trees. In general, interaction trees are given in Coq as a co-inductive type, but it's useful for our purposes to think of it as as largest solution of a particular equation. And this equation has three components. So the first one is the ground type, which we pick to be integers, but we can pick any ground type there. The second component represents a silent step or an internal step of computation, which is needed for technical reasons. And finally, the third component is actually used to represent effects. So each effect I comes with an input arity, which represents the argument, and the continuation, which sends the output arity to interaction trees. So for example, for the input operation, the output arity is a type of natural number. So the continuation is going to be, just functions from natural numbers to interaction trees. And this is exactly, what represents the branching. So now, suppose we want to add higher order computations or higher order effects to this. Well, what we could do is we can just add another component to the equation. But this is not going to work, because in this equation, we're going to have negative occurrences of recursion. And so this equation does not determine an inductive or a co-inductive type. So we cannot solve this equation using inductive or co-inductive types. So our idea is to go into a more extensive setting, specifically guarded type theory, where we know how to solve equations like this. All right? And well, if you don't know about guarded type theory, it's not really important. The only thing that you need to know is it's a kind of type theory where you have a particular functor later, which we denote with this black triangle. And the two important bits in guarded type theory is that we have guarded recursion using this kind of guarded fixed point combinator. And what is even more important for us is that we have unique solutions to all guarded equations of types. So to equations of the form x equals f of later x, where this later x can appear in any position, both in negative and in positive positions, but this x has to appear under the later modality, so this makes it guarded. Right, so now with this, we can actually define our type of guarded interaction trees as the unique solution to a particular equation. And here we can see we still have a number of components. So we still have the component that corresponds to ground types, which again, for simplicity here, we take to be natural numbers. We have a component that corresponds to a silent step of a computation. And we have a new component that corresponds to functions to represent higher order computations. And this here you can see this component is guarded. So we are looking at not just functions from guarded interaction trees to guarded interaction trees, but from later interaction trees to later interaction trees, right? And we need this to make sure that this equation is actually guarded. Also, we add another component that corresponds to representing explicit error states, will be quite useful. And finally, we have the component that corresponds to representing effects. And here you can see we modify the input and output ariths so that they also take the type of guarded interaction trees as an argument. And this is necessary for representing higher order effects. So for example, if you want to represent higher order store, we want to have operations read and write. So for example, the read operation takes a location and reads the value that is stored at this location in the heap, and it produces an interaction tree. And so if you want to model those kind of effects, you need to modify the input and output ariths to allow this. So this is quite a crucial change. Now, with this definition, we can actually we can interpret untyped lambda calculus with effects. So we have the combinators that allow us to embed, natural numbers, functions. We have a combinator that computes function implication, and so on. However, the effects are not really interpreted. They're just represented as is. Those are effects without handlers or whatever. But in order to give full meaning, to full semantics to the guarded interaction trees, we actually need to be able to interpret those effects. And we do so as follows. So we assume that every effect signature comes with a reifier. So what we mean is that for each effect signature, we have a type state, which represents the internal state that we need to interpret the computation. And then for each operation, we have a reification function, which essentially computes the output arity from the input arity using the state monad with this internal state parameter. And one way to think about it, it's quite similar to what Ugo described in the first talk as like this generic effect handlers, right? So we don't involve the continuation at all, we just compute the output arity from the input arity. And if we have those reifiers for all the effects, then these determine reduction relation on guarded interaction trees, or rather on pairs of guarded interaction trees and this internal state parameter, which tells us how to execute those operations. So for example, for the higher order store, we can take the state parameter just to be the type of maps from locations to later of guarded interaction trees. And if we write down the reifiers, in the most standard way, then we get the kind of reductions that we expect. So for example, if we have a guarded interaction tree that first writes alpha to the location L and then proceeds as beta, and we are looking at this tree in the state sigma, then this reduces to the continuation beta, and it results in an updated state where we actually assign alpha to the location L. Okay, so this gives us the semantics of guarded interaction trees, and we actually want to reason about the semantics, to reason about the behavior. And my favorite way of doing this is through making a program logic. So more specifically, what we do is we make a separation logic for guarded interaction trees based on iris. For those who don't know, iris is a powerful high-order separation logic with an extensive formalization. You might have heard about it during some other talks in POPL', like there were some sessions yesterday and probably today as well. But basically, you can think of it, it's a framework that allows us to derive custom separation logic for different use cases. And in our work, we instantiate iris with the guarded interaction trees, and we get a separation logic. So we get all the usual connectives like separation, conjunction, magic wand, and so on. But of course, the most important connective is the weakest precondition. And so the weakest precondition for a guarded interaction tree alpha and the predicate phi, it states that, first of all, this guarded interaction tree alpha is not an error, it's not in an error state. And whenever it reduces to a value, so whenever it cannot reduce any further, this value is going to satisfy the predicate phi. And this is a quite reasonable, quite standard reading of the weakest precondition, similar to what you would expect from separation logic for a normal programming language. And in fact, in our separation logic, we have all sorts of normal rules, structure rules that you would expect. But of course, the most interesting rule of our program logic has to do with the facts. So here I have the version of this rule for effects that is specialized to the right effect. So here, once again, we have this computation that writes something to location L and then proceeds as beta. And if you want to prove something about it, we need to prove two things. So first of all, we need to provide a predicate has state, sigma, which says that the internal state for this store effect is sigma. And the second thing that we need to do is we need to provide a proof of beta, so of the continuation, assuming that we have an updated state, where we actually written alpha to the location L.
5 minutes
Now, so this is a symbolic execution rule for the right operation. And those of you who are familiar with separation logic might be thinking that this rule looks very suspicious. And this is because it talks about the whole heap sigma and not just about this specific location L. But luckily, using the mechanisms of Iris, we can derive the more standard rule, which we call the local rule, which talks just about the location L and not about the whole state sigma. And I just want to stress out that we can derive this just in Iris without knowing anything about guarded interaction trees and so on. And in fact, we can completely recover the standard looking separation logic for imperative programs just from this one generic rule and the logic that we have. And I guess the point that I want to make here is by utilizing Iris, we can derive different domain-specific logics from different effects just from one separation logic that we have for guard interaction trees. And of course, we have to have this global version of the rule because, well, in this case, we know that sigma is a heap, so we know how to separate it into individual locations, for example. But if we're talking not just about store, we're talking about arbitrary effects, this parameter sigma is just some state that is provided, that is decided by the user. So the logic doesn't know how to split the sigma into different things, so it's up to the user to do this work. But luckily, the user can do this without breaking the abstraction of the program logic or anything like this. All right, so now we can finally put all these components together in one of the case studies that we did. And this is a case study about cross-language interaction, which I think showcases kind of the nice thing about domain theory and the nice thing about the modularity that we did. And the setup of this case study is as follows. So we have two programming languages. So first of all, we have lambda calculus, simplified lambda calculus with recursion, integers, and input and output operations. And the second programming language that we have is affine, or linear lambda calculus, where we have linear functions and linear references with like strong update and things like this. Now, we can interpret both of those languages separately in guard interaction trees. And once we interpret them in the common target, we can start talking about, okay, how do those things interact in terms of their semantics? But of course, we have to facilitate their interaction somehow. And we do this through these two embedding functions. So these embedding functions allow us to move values between two languages. But of course, we cannot just, for example, take a linear function from one language and use it as a normal function in a nonlinear language. So when we move values between languages, we have to protect them. So for example, if we move a function, we have to wrap it in some kind of runtime check that monitors linearity violations at runtime. And now the question that we want to settle about this system is that we want to prove that this combination of languages with the embeddings is memory safe. And this is how we do it. So first of all, we prove separately that the interpretation of the two separate languages is safe. And we do this by constructing two separate logical relations models using the program logic that we described before. And we do this completely independently of each other. Then we prove that the embedding functions actually move those things between the models in a memory safe way. So what we mean by this is that embedded terms, they can raise errors, but the only error that it can raise is a linearity exception. So an embedded term cannot raise a memory error, for example. It cannot dereference a null pointer or something like this. Then we combine those things together to prove that the combined system with embeddings is memory safe. And we do those just by combining the logical relations from the first two points and the proof of the third point into one model. And I want to say that when I say combine, I don't mean it as a metaphor. I don't mean it, in some abstract way, like the proofs are similar or something like this. No, I mean it in a very direct way. So we formulate the first two models separately and independently of each other. They don't know of each other. And then we can put them together, literally reusing, the same definitions, proofs, and co-identifiers. And we believe that, well, this generally allows us for a great proof reuse, and we believe this validates the sort of the modularity of our approach. So, well, since it's already the break time, I would like to thank everyone for listening. If you want to look at more examples and details, please check out our formalization and our paper, and I would be glad to take your questions.
Thank you very much. The break has just started, but I think we can still take some questions. So,
hi. Thank you for a lovely talk. One of the things that you had on slide, I think 4 or 5, was that there's a silent step for your interactions trees. Could you give us some intuition as to why that silent step is needed in there?
So I can give you. So a more philosophical reason is that, well, for guarded interaction trees, or for interaction trees in general, we want to talk about things like, compare programs modular some kind of internal steps. There's also a more technical reason for this, is that, so because our functions are guarded, when we apply a function to an argument, the result, we don't get an interaction tree, we only get later of the interaction tree. And then, so then we need to embed this somehow, interaction tree, into the general type, and this results in kind of a silent transition.
So there is an online question. Do you need this higher-order constructor to model higher-order functions, or rather higher-order effects? I thought we could do higher-order functions with first-order trees, as in game semantics, for example.
Yeah. So we need this function for for representing functions. We need this for representing higher-order functions in a more in a semantic way. You can still, there are some tricks that you can do to represent higher-order computation interaction trees, but this involves working with closures, or, I mean, it involves some kind of syntactic techniques, where this is just a more straightforward semantic way of doing this. But more importantly, for higher-order effects, not just for computations, this corresponds to having, this interaction tree parameter over here.
Okay. Go, Steve.
Sorry, this is Steve Zdanswick from Penn. Thank you for the very nice talk. One of the benefits of interaction trees is that you can extract executable programs from them, but I noticed your handlers were into prop, so I'm wondering what the story is for extraction of executable programs is for guarded interaction trees.
Right. But so our handlers are not actually into prop, so they're just calc functions, let's say, but nonetheless, we still have some problems with extraction, and this mainly has to do with the fact that we're working with this guarded type theory on top of calc. We have a hunch that it is possible somehow to, abuse the calc extraction mechanism hard enough to be able to extract this stuff, but we haven't been able to actually do this in practice, unfortunately.
I have a question. So you had this restriction on, I think you called them the arrayifiers.
Yeah.
Have you thought about relaxing that? Could you do, I don't know, things like concurrency or using continuations multiple times?
So, yeah, so that's a very good question. So indeed, right now, our verifiers or handlers or interpreters, whatever you want to call them, they are very restricted. If we allow the verifiers to also handle the continuation, to do something with it like discard it and so on, then we will be able to model things like, continuations and so on. But this will introduce some changes to the logic and we limit some of the reasoning principles that we have. So this is something that we definitely want to look into, but we haven't done that.
Okay. Thank you very much. One last question.
Hello, I had a quick question about, I was actually going to also ask about control effects as well, but I was also wondering, the domain of interpretation seems to be fixed in this case. Is there ways to generalize it, or was it fixed for examples in this setting? So is there also a reason why you added the error node for this case?
Yes, it did. So you're completely right. This is a fixed domain, just like you would expect in domain theory for untyped lambda calculus. And this is also the reason why we have this error domain, because we might have some kind of error. So for example, if you take a natural number and we apply it to another natural number, that results in error, right? Because we can only apply functions to arguments, and that was more of like a design choice that we wanted to have like one universal domain where we can interpret all sorts of stuff.
Okay, thank you.
Thanks. Let's thank the speaker again.
Thank you, Sam, for doing this.